KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.com.
In continuation to the last class, in this class we start with the gravitational constant. The gravitational constant, which is actually we are representing with a letter capital G, right? So this is what capital G, okay, right. As we discussed in our previous classes, Newton's law of universal gravitation. Newton's law of universal gravitation, that is from the statement given by Newton. So what is the statement, ma? So the attractive force, right, in this entire universe, in this unimaginable space in our surroundings, that's we are calling it as universe, any two bodies, right, every two bodies or any two bodies attracts with certain amount of force. That's what we are saying, that the attractive force, right, the attractive force between any two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is the statement given by Newton. Okay. From this statement, mathematically we also written many times F is equal to G into mm by r square. Otherwise, F is equal to G into capital G into m1 m2 by r square. But here one thing we have to remember, that is what actually F is directly proportional to the product of their masses, means whatever it may be the two bodies, right? Whether the two bodies are two celestial objects present in the universe or whether the two bodies which are present on the surface of earth. So whatever they may be. But the thing is, the attractive force between those two bodies is directly proportional to the product of their masses. That is what m1, m2, and inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. Okay, right. So from this, you can mathematically, you can say that F is directly proportional to m1, m2, and F is inversely proportional to r square, small r square. Small r is the distance between those two bodies, between what we are going to calculate, or we are in a discussion about the gravitational force. Okay, right. So to remove the proportional constant, as I told just now, F is directly proportional to m1, m2, and F is directly proportional to 1 by r square. If you join these two, then F is directly proportional to m1, m2 by r square. Suppose if you want to remove the proportion constant, we are going to add some constant, that is what capital G. Including the constant, you can write the expression for gravitational force as capital F is equal to capital G into m1 m2 by r square or mm by r square. So mm means one is small m, another one is capital M, right? But here is not a matter what is the notation, but anyhow we have to keep in mind, from Newton's law of gravitation, we have to keep in mind, in this entire universe, every two bodies attracts with certain amount of force. The magnitude of this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. right? For this, mathematical expression is F is directly proportional to m1 m2 by r square. To remove or by removing the proportional constant, capital F is equal to capital G into m1 m2 by r square, right? Okay. Here capital G is the universal gravitational constant. Capital G is the universal gravitational constant, right? In this class, in today's class, now we are going to discuss about universal gravitational constant. Universal gravitational constant. Okay, right. See here, the value of the gravitational constant capital G. The value of the gravitational constant capital G entering the universal law of gravitation can be determined experimentally, and this was first done by English scientist Henry Cavendish in 1978. Okay, so you observe carefully, the value of the universal gravitational constant, otherwise the value of the gravitational constant capital G entering the universal law of gravitation can be determined experimentally, and this was first done by English scientist Henry Cavendish in 1798. Full stop. The apparatus used by him is schematically shown in figure, right? This is what the figure, okay, right. And what I am saying is, see, not only here, everywhere in our physics, when we are going to remove the proportional symbol, right, there automatically we are getting some constant. Sometimes constant may be 1, that will be different situation. So here we are getting the constant in case of discussion of attractive force between two bodies in this universe. That constant is gravitational constant, okay, and some constant having some value, right? So this gravitational constant also having some value. Here the question is how to determine that value. How can we determine the value of universal, the value of gravitational constant? The value of gravitational constant, okay, that is right. The value of the gravitational constant capital G entering the universal law of gravitation can be determined experimentally, and this was first done by English scientist Henry Cavendish in 1978. So to do this task, he used one apparatus. That is the apparatus here he has given, right? So what is this operator and what is present here? See here, schematic drawing of Cavendish experiment, right? S1 and S2 are large spheres. See, this is S1, this is S2, right? S1 and S2 are large spheres which are kept on either side. See here, this is 1 and this is 2, S1 and S2, okay, right. Which are S1 and S2 are the large spheres which are kept on either side of the masses at A and B. Full stop. When the big spheres are taken to the other side of the masses, right, shown by the dotted circle, see here. So it is the solid lines, it is the dotted circle. So when we are taken these two to other side, so this is to there and this is to here. When the big spheres are taken to the other side of the masses, the bar AB rotates a little since the torque reverses direction. So what is torque here? That we discussed in the chapter of rotational motion, right? So torque tau is the product of force and the perpendicular distance between the point of action of force and the point of application of the force, right? Point where we are going to apply the force and the point about which the body is going to rotate. As simple as such, r bar position vector is the perpendicular distance between the axis of rotation and the point of application of force, right? So this is what we discussed in the chapter of rotational motion. So mathematically tau bar is equal to r bar cross f bar. r bar is the perpendicular distance between the axis of rotation and point of application of force, and f bar is the applied force, right? So you can take either magnitude and direction or direction, because force is a vector quantity, right? So tau bar is equal to r bar cross f bar, right? It is also a vector quantity. I know, just by using right hand rule you can determine the direction of the torque. Okay, right. See here, the bar AB has two small lead spheres, right? So I already told you about this picture, and that is what here, when the big spheres are taken to the other side of the masses. So first big spheres are here. When these big spheres are taken to the other side of the masses, right? Other side of the masses, the bar AB rotates a little since the torque reverses direction. Full stop. The angle of rotation can be measured experimentally. The angle of rotation can be measured experimentally. Okay, right. So here he is also showing the direction in which that is going to rotate. Okay, see this, Now he is going to descript, and here he is going to explain how he calculated the value of universal gravitational constant, that is capital G. Okay, see this. The bar AB has two small lead spheres attached at its ends. The bar AB has two small lead spheres. The bar AB has two small lead spheres attached at its ends, right? Now, the bar is suspended from a rigid support by a fine wire. So it is a rigid support, and it is a wire. It is a wire. Okay, right. Two large lead spheres are brought close to the small ones. Two large lead spheres are brought close to the small ones, but on opposite sides are shown. See here, opposite sides only, right? That is, the big spheres attract the nearby small ones by equal and opposite forces as shown. So here, what is the attractive force between the two bodies, and what is the attractive force by one of the body on other. Similarly, what is the attractive force by other with respect to the first body, right? This is what here we also keep in mind. What is Newton's third law, right? Action is equal to minus reaction. For every action there is an equal and opposite reaction. So here, to calculate the attractive force, suppose for example there are two bodies, for example PQ. What is the attractive force by P on Q? What is the attractive force by Q on P? So to calculate the attractive force between these two bodies, basically we have to use Newton's law of gravitation, that is F is equal to G into mm by r square. But after that, because F is a force is a vector quantity, along with the magnitude, it also has direction. So even though the direction is not same, how can we say that force is same? It is impossible to say. That's why here we also keep in mind the Newton's third law. Okay, right. Now see here, the big spheres attract the nearby small ones by equal and opposite force as shown, right? Now there is no net force on the bar, but only a torque which is clearly equal to F times the length of the bar, right? So while explaining about the rotational motion and while talking about the torque in the chapter of rotational motion, I explained with many examples, right? For example, that is what water bottle. So when you are going to open the water bottle cap to drink some water, so you are going to apply two forces. You are going to apply two forces, but these two forces constitute a couple. Couple means two. Then finally these two forces leads to exert certain amount of torque on the cap, that is tau is equal to r bar cross f bar. R bar cross f bar. Okay, right. So that's why he is saying there is no net force on the bar, but only a torque which is clearly equal to F times, F times the length of the bar. F times the length of the bar, where F is the force of attraction between a big sphere and its neighboring small sphere, okay. So that's you have to keep in mind. So what is the big sphere and what is the small sphere? How we are calculating the gravitational force, okay, right. See this one. So once again I am saying here, this point is important, you just please understand, and also you have to memorize. That is what the net force is 0, but torque is present. That is only he is saying there is no net force on the bar, but only a torque which is clearly equal to F times, right, which is clearly equal to F times the length of the bar, where F is the force of attraction between a big sphere and its neighboring small sphere, okay, right. Next, due to this torque, the suspended wire gets twisted till such time as the restoring force of the wire equals to the gravitational torque. Here, in the chapter of laws of motion, I told you how the body is balanced. But in that chapter, I didn't discuss the torque, but I explained you how the body is in equilibrium under the action of various forces, okay. But here, it is not that. Here the torque is important. Right? But anyhow, the body is in. So now itself we have to memorize once again rotational equilibrium. That's what we discussed in the chapter of rotational motion. Okay, right. Due to this torque, the suspended wire gets twisted till such time as the restoring torque of the wire equals the gravitational torque. Restoring torque and gravitational torque, right? So restoring torque means what? In the chapter of mechanical properties of solids. Sorry for saying here, because that is our next chapter, okay. But here I want to say that the material property of a wire, which provides restoring torque, but that rod is present on surface. So because of the gravitational force, so the gravitational torque will exert. So here these two are going to balanced. See here, due to this torque, the suspended wire gets twisted till such time as the restoring torque of the wire equals the gravitational torque. Full stop. Now see here, if theta is the angle of twist of the suspended wire, right, the restoring torque is proportional to theta, equal to tau into theta, where tau is the restoring couple per unit angle of twist. Right, again I am coming back. See here, if theta is the angle of twist of the suspended wire, the restoring torque is proportional to theta. What is theta? Is the angle of twist of the suspended wire. Then restoring torque is proportional to theta, equal to tau theta, where tau is the restoring couple per unit angle of twist, full stop. Tau can be measured independently. For example, by applying a known torque, right? Here tau can be measured independently. For example, by applying a known torque and measuring the angle of twist. Okay, full stop. So from here to here, he is talking about how the restoring torque is proportional to theta, right? And then which is equal to tau theta. What is the tau means? It is the restoring couple per unit angle of twist. And he is also saying that tau can be measured independently. Right, now example, by applying a known torque and measuring angle of twist, full stop. The gravitational force between the spherical balls, spherical balls is the same as if their masses are concentrated at their centers. The gravitational force, right? The gravitational force between the spherical balls is the same as if their masses are concentrated at their centers. This is what here you have to recall. What is center of mass? In the chapter of rotational motion, I told you, center of mass is an imaginary point where the total mass of an object supposed to concentrate. So here also the spherical balls are behaving like that. The spherical balls are present like that. Not only he is saying the gravitational force between the spherical balls is the same as if their masses are concentrated at their centers. Thus, if D is the separation between the centers, of the big and its neighboring small ball, centers of the big and its neighboring small ball, capital M and small m, their masses, the gravitational force between the big sphere and its neighboring small ball is, the gravitational force between the big sphere and its neighboring small ball is F is equal to G into mm by d square. Capital F is equal to capital G into capital M into small m by small d square. Okay, right. If L is the length of the bar AB, then the torque arising out of F is F multiplied by L. At equilibrium, this is equal to the restoring torque, and hence capital G into mm by d square. This is what F into L is equal to tau into theta. Okay, right. Now this is the torque due to the gravitational force. This is the torque due to the restoring ability. That is what restoring torque and gravitational torque both are equal when the rod is in equilibrium. When the rod is in equilibrium, when the bar is in equilibrium. So at equilibrium, this is equal to the restoring torque, and hence you can write this now. Observation of theta thus enables one to calculate capital G from this equation. Observation of theta thus enables us to calculate capital G from this equation. So how can we calculate? See this. Since Cavendish experiment, the measurement of capital G has been refined, right? The measurement of capital G has been refined, and the currently accepted value is. Suppose once you go back to this formula, because he told that we can calculate G from this expression now. Why? Because this small m and capital M and D and L and tau and theta, these are all known values for us. So by doing the experiment, you can get the tau value, you can get the theta value, right? And by using that Newton's law of gravitation, this relation already we know, that is F is equal to G into mm by d square. So that's why from the experiment and some of the constant values, that is what capital M and small m is like constant values. No, we need not to bother about these things separately, because these values already known before doing the experiment also. What is capital M, what is small m, what is capital L, and what is D, that's you know. So by substituting these known values, you can calculate capital G value. That is, capital G is equal to 6.67 into 10 to the power of minus 11 Newton meter square per kg square. Newton meter square per kg square. Okay. So in this manner, we can calculate universal gravitational constant value. That is capital G. So present accepted value, currently accepted value is G is equal to 6.67 into 10 to the power of minus 11 Newton meter square per kg square. Okay, right. So how we did this experiment and how we calculated? Just by taking some of the masses and by taking one of the bar AB, and the length of the bar is L. That's what we assume here. This credit, so whatever the discussion we had today, this credit goes to the scientist, great scientist Henry Cavendish. Okay, by taking the bar AB and small lead spheres attached at its ends. Okay, and with the help of this you can see the experimental setup or experimental arrangement here. That's what I drew on the board. See here now. So because of the small masses and big masses and the gravitational force, and finally here regarding the torque, because torque is nothing but the product of force and perpendicular distance. Suppose in case of rotational motion means perpendicular distance is the it is the perpendicular distance between the axis of rotation and the point of application of force. But here in our discussion is a product of gravitational force and length of the ball, that is capital L. No, so this is what torque, and another side it is what rotational torque, that is restoring torque. Sorry for this, restoring torque, which is tau into theta. Okay, right. Now by taking that, applying the known torque and measuring the angle of twist, see the gravitational force between the spherical balls is the same as if their mass is concentrated at the center of mass, at their centers, right? Thus if D is the separation between the centers of the big and its neighboring small ball, capital M and small m their masses, the gravitational force between the big sphere and the neighboring small sphere, right? Okay, neighboring small ball is, okay, F is equal G into mm by d square. When this is the force and if L is the length of the ball, this is the gravitational torque. Okay, that is equal to, this is what here rotation restoring torque, tau into theta. Observation of theta thus enables one to calculate capital G from this equation. Since Cavendish experiment, the measurement of capital G has been refined and the currently accepted value is capital G is equal to 6.67 into 10 to the power of minus 11 Newton meter square per kg square. Okay, right. So this is what the way, this is what the procedure, what Henry Cavendish followed to calculate or to set up or to determine the experimental value. That is what for capital G, 6.67 into 10 to the power of minus 11 Newton meter square per kg square. Okay, right. So in our next class we will continue with the next continuation topic. Thank you.